We are now going to look at specifically the sampling distribution of the statistic xbar, the sample mean in samples of n observations from a population. So consider a population with a variable x quantitative that has mean mu and standard deviation sigma. The sampling distribution of the statistic xbar in repeated samples of n observations from this particular population is a probability distribution with a mean equal to mu, the mean of the population from which the sample came. When you take a random sample of n observations from a population, the sample mean xbar might be a little bit larger than the population mean mu, or it might be smaller than the population mean mu, but it is correct on average. And this is very important because it tells us that the statistic xbar is a reliable, trustworthy estimate of the parameter mu. Another property of the sampling distribution of xbar is its variability. The standard deviation of the sampling distribution of xbar is equal to sigma over square root of n, where sigma is the standard deviation of the population. What this tells us is that sample means vary much less than individual observations in the population, and that larger sample sizes give us sample means xbar that tend to remain pretty close to the value of the population mean mu. The implication of this is that the statistic xbar is also a very useful estimate of the population mean mu. So those properties of the sampling distribution of xbar can be demonstrated mathematically. We are also going to see that in action through simulations. We've seen this simulation before. This particular tool contains 3 panels. At the top, the distribution of the population. In the middle, the distribution of the actual sample data in one random sample of n observations. And at the bottom, we see in succession the accumulation of all the sample means xbar for each random sample from this population. The population is a model for the distribution of IQ scores in the general population, a normal distribution with mean mu 100 and mean standard deviation 15. In this simulation, we will see 3 different cases. The sampling distribution of xbar when we take random samples of size 8, another simulation where we take random samples of size 40, and then another simulation for random samples of size 200. We start with taking random sample of 8 observations. We have the histogram, another set, and another set. And each time we calculate the sample mean xbar, and then we plot all those xbars. And we can simulate doing that many times, here 1,000 times. And we get the beginning of the sampling distribution of xbar. It's a roughly normal distribution, fairly wide. What happens if we consider random samples of 40 observations? Distribution of xbar is still roughly normal, but narrower. For random samples of size 200, we see that the distribution of all those sample means is really very narrowly clustered around the value of 100, the mean of the population, and still has this roughly normal distribution. All 3 examples illustrate what can be shown mathematically, that is that the distribution of sample means, the sampling distribution of xbar, is centered around the same value as the mean of the population, and also that sampling distributions will be narrower for larger sample sizes than for smaller sample sizes. The simulations we just watched took random samples from a normally distributed population, and we ended up with sampling distributions of xbar that were all normally distributed. What happens to the sampling distribution of xbar when we take random samples from populations that are not normally distributed? What can we expect then? This very important, the central limit theorem, tells us that for large enough sample sizes n, the sampling distribution of xbar will be approximately normal, and that how large size n we need to consider depends on the shape of the population. The exact value of the sample size you need will depend on the exact shape of the population. What can be shown with simulations trying out all sorts of population shapes is that large enough can be just as low as 10 or more if you consider populations that are symmetric, but that large enough would have to be at least 25 if you consider populations that are skewed but not extremely skewed. and that if you consider populations that are extremely skewed, then you might need to consider sample sizes of at least 30 or maybe even at least 40 to count on the sampling distribution of X bar being approximately normal. Those are not firm boundaries. Those are guidelines based on simulations trying out all sorts of population shapes. Let's actually try it out. We are now going to do similar simulations, but for 3 completely different populations. The first one will be normal. The second one will be also symmetric, but not normal, a uniform distribution. And the third one will be a skewed distribution called an exponential distribution. So let's start with the normal distribution for the population. Now for the uniform distribution, now for the clearly skewed population with an exponential distribution, you can see that actually in the middle panel, all those random samples are clearly skewed because we take them from a skewed population. And the sampling distribution for random samples of 10 is still skewed, not as skewed, but it is not a normal distribution. There's clearly more area on the right tail. What if we take random samples of size 40? Those random samples are still skewed, like the population, but the sampling distribution at the bottom panel, well, it looks very close to normal. That's the central limit theorem. What we can see here is that regardless of the shape of the population, every time we built by simulation a sampling distribution, the distribution of values of X bar was centered on the mean of the population. And we also noticed that when we considered larger sample sizes, that sampling distribution was narrower than when we considered smaller sample sizes. The central limit theorem showed us that the shape of the sampling distribution depends on a mix of the shape of the population and what kind of sample size we are considering. This is a summary of similar simulations by a different program, showing you what happens when you have a population that is either normal, uniform, or exponential, and considering sample sizes that are as small as just 2, 10, or 30. And again, what we see is that there is always a sample size that is sufficiently large that the sampling distribution of X bar can be counted on to be approximately normal. And that's the amazing usefulness of the central limit theorem, because it will give us a known probability model, a normal curve, for the sampling distribution of the statistic X bar.